So I'm going to talk about channel charting, which is a machine learning approach to dealing with channel state information statistics. I'll start with the basics. When we model the physical layer of wireless communication systems, we have this simple model with this linear model, and we have this equation where Hn here stands for the channel state. And in this presentation, I'm going to actually focus not on this transmit-receive chain, but specifically on H and on the statistics of H. So assume that I have a system and I have already set up some channel state information, channel state acquisition system, which I'm not going to describe. And this thing works as intended. And I just observe H and try to make use of the statistics of that variable. And I don't know anything a priori about the statistics, in fact. If you think of the classical way of dealing with that, what we do typically is that we postulate a model. Here's an example. This is you can postulate that the channel follows this model, for example. So here I have a channel with L path, and each path is actually represented by a planar wavefront, which is arriving under the angle of incidence theta, and this planar wavefront is going to hit the first antenna and then the second one a little bit later, and so on. And if I have a uniform linear array, as we all know, the array response here will look like a bunch of complex exponentials, like, phase shifts, which are due to the incremental delays with which this wavefront is hitting my antennas. So I'm sure you know already about this if you work with physical layer signals. So what I want to point out here is that when we do that, I postulate the model, and what is left to estimate, if I want to estimate the channel, is to estimate the parameters, the gains alpha and the omega, possibly the number of paths, right? So here I postulate the model, I only estimate the parameters. With channel charting, we want to do things differently. Channel charting is a data-driven approach, and what we want to do is we want to be able to estimate both the model and the parameters. So how can we do that? Because this was a quite trivial model. In reality, we typically have much more complex situations, such as the one which is represented here. Between the single transmitter and the intended receiver, I have a bunch of scatterers. They have usually very complex geometry. I don't know a priori the permittivity of all the scatterers and so on. I know very little about their position. So if I had a complete description of the scene, I could try and model this, and this is what we do with ray tracing simulators. But in fact, this approach is not really practical if you don't have very accurate prior information about the geometry of the problem. So we want to actually replace that approach with so-called self-supervised approach, which is channel charting, and I'm going to tell you how this can work actually. So channel charting is based on dimensionality reduction. From a very abstract level, let me tell you a bit about dimensionality reduction. I'm going to do that using a data set. Here's an example. So let's say that this is a data set. So what is represented here is a three-dimensional space. So which means that every sample in my data set is going to have three components, so three real components, right? So every time I get a sample, I look at these three components, and this gives me the coordinate of that sample. So here I'm picturing a whole bunch of samples. This is my whole data set, right? And what I see immediately is that these samples, they do not occupy the full space. There are some areas in my in my space, in my variable space, where I never get any samples. And in fact, if you if you look closer, you see that although my samples live in a three-dimensional space, I could actually parameterize this sort of ribbon shape using only two parameters, and I could represent the location of any sample in that data set using only two real parameters. So that is the idea behind dimensionality reduction. We're going to have, in general, a data set in high dimension, much higher than 3, but I'm just using 3 because I can represent it. And we are going to try to associate to each sample some coordinates in a low dimensional space. Okay. So here you can see that all my samples are colored, and the reason why they are colored, so the coloring is arbitrary here, and is just there to show you where these samples will go in the reduced dimension space. So in order to make this dimensionality reduction work, we use the concept of manifold. What is a manifold? So the ribbon that I was showing before is a manifold. In general, a manifold, so this is another example of a manifold, this sphere. A manifold is any space which can be locally approximated by a Euclidean space. And if you look if you look at one point on the surface of Earth, you can see that it can be approximated by some flat surface, all right? And we are actually going to use that property that locally manifold can be approximated by a Euclidean space. So the underlying assumption in dimensionality reduction is that the data set lies on a manifold. I know nothing about this manifold, but it lies on a manifold, and the goal is to try and identify it. So here's, in one picture, here is what we are trying to do. We have a data set that lives in high dimensional space, and to each sample we want to associate some, in that example, two-dimensional coordinates. Of course, there are many ways to do this, so the problem is a little bit ill-posed if I don't say anything more than that. What I actually want to do is I want to preserve the neighborhood relationship between my samples. So I want that two samples which are neighbors in the original data set, they should also be neighbors in the reduced dimension data set. And this is why I colored them, so you can check that. Two neighbor samples in that data set, they have almost the same color, and they and here they end up having also almost the same color, which means that this neighborhood relationship is preserved. So dimensionality reduction is a continuous version of clustering. I know many people are familiar with clustering. In clustering, you have finite number of classes. What we are trying to do here is kind of similar, except that we have a continuous variable which represents all the possible classes. So far I have stated the objectives, but it's not very clear how to perform this. And I have to say, when I first approached this problem, it looked a little bit like black magic. How can you actually achieve that and program a computer to do it? So I'm going to show you one algorithm that actually performs dimensionality reduction. So, and in order to do this, I'm going to take a detour. I'm going to talk about another algorithm called multidimensional scaling. Let me tell you what it does. Suppose that I'm given a set of distances between a bunch of cities. So here you have a list of cities in Europe, and you have the same cities on the columns of this table, and what you have in each cell of the table is the distance by road between these pairs of cities. So suppose I am given only this. I've never been to Europe. I don't know anything about geography, and I am only given this. And I could start from this table and ask you to assign two-dimensional coordinates to each of these cities under the constraint that these coordinates, they should fulfill in the best possible way these pairwise distances constraints, right? So that's very easy to write. This is the so-called multidimensional scaling algorithm. This is what it does. So if you actually program this algorithm and look at the solution, you may get something like this. So now, if you are familiar with the geography of Europe, you will see that east and west are pretty much okay here, but north and south are flipped. And of course, it makes sense, because if all I give you is this table, actually, you can find a whole bunch of solutions which will be equally good according to this to my original metric. Because if I take any solution and I flip it or I rotate it, I don't change the pairwise distances, right? So if all I know is this is a perfectly acceptable solution. And we are going to have this property again in the channel charts. Okay, so this is multidimensional scaling, but how is this related to channel charts? Okay, let me skip the math behind it. So now I want to talk about an algorithm which actually performs dimensionality reduction. So here I have, I start from the same example as before, this so-called Swiss roll data set, which is this ribbon here. I have generated a bunch of random realizations, and I'm going to select an arbitrary distance threshold between samples of this data set. And when two samples, when the distance between two samples is below this threshold, I'm going to link these two samples by an edge. So I'm going to form a graph. So if I choose this threshold appropriately, I may get something like this. This is my graph, right? So maybe you kind of see it coming now. This graph sort of captures the shape of the manifold. Once I have this graph, I'm going to compute the pairwise distances between any two samples, except I'm going to compute this distance on the graph, not the Euclidean distance, but the distance on the graph. So let me show you one example. I select, for instance, these 2 points. The Euclidean distance would be, of course, a straight line, but I don't do this. I take the shortest distance on the graph, which happens to be this circuit here. And as you can see, this is an approximation of the geodesic distance on my manifold. So I do this for all pairs of points in my data set, and I get this gigantic, two-dimensional table, very similar to what I showed before. And then I can apply multidimensional scaling, actually a slightly modified version of multidimensional scaling that only takes into account the distances between the neighbors. And this is going to yield low-dimensional coordinates associated to any sample in my original data set. So this is, I didn't say how to pick the distance threshold when you construct the graph, and this is a critical parameter. There are no known good ways to do this. And there is also one catch, which is if there is a spurious sample, which happens to be like in the middle of the two folds of the ribbon, you may actually have a spurious short circuit between the two folds, right? And a single point, misplaced point, if you have such a short circuit, that's going to affect all the pairwise distances on the graph, and is going to completely kill the result that you get. So this is it's not very robust. A single misplaced sample can completely destroy the whole structure, right? So in practice, we are not going to use this. I'm just presenting this to give an intuition of dimensionality reduction approaches. So in practice, we are actually going to use neural networks. Artificial neural networks, of course. I don't know why we tend to forget the artificial, They're always artificial. So it's going to work like this. I have my input samples. I put them at the input of some artificial neural network, and I get a reduced dimension representation. So of course now the question is, how do I train this neural network? So there are many ways to train those. Various architectures have been considered. One of them is well known, is the autoencoder. So here I don't have one neural network. I have two neural networks. The first one is trying to reduce the dimension, and the second one is trying to do the opposite, which is trying to reconstruct the original data from the low dimension representation. Right? So if you actually look at the loss function here, the loss function is based on the distortion between the original value and the reconstructed value, which is not exactly what I wanted. You know, in the first place, I said I want this representation here to respect the neighborhood relationship, but my loss function is not including the y's here, so it's not exactly the right approach, and you will see that it sort of works, but not so well, which makes sense. Well, you know, my loss function is not the right one. The other thing that you can do is to consider Siamese networks. So here I also have two artificial neural networks, but they are identical. I put two different samples at the input. I get two representations in my latent space, and my loss function actually is closer to what I wanted in the beginning. I want the distance between these two here to be approximately equal to the distance between the two samples at the input. So this is actually closer to what I want. However, these two approaches, they have a common drawback, which is that they both rely on this distance in the ambient space, right? So if I talk about channel state information, the ambient space has pretty high dimension. Think of number of antennas at the receiver times the number of antennas at the transmitter times the number of subcarriers. This can be quite high, and we know that when we deal with high dimensional random variables, if you try to compute the Euclidean distance in high dimensional spaces, this distance is dominated by noise. So it's not very accurate. And I'm sure that if you have any intuition about the physical layer, you know pretty well that even if you have two channel measurements which are measured more or less in the same situation, like let's say same location, but you do the measurements twice, and then you just take this very long CSI vector and you subtract them from each other, you know, the difference will not be close to zero, right? So in fact, this is an issue because all the methods I have presented so far, they rely on the fact that this distance here is meaningful, but in reality it's not. So at some point we realized we have this problem with the distance. The Euclidean distance which we are trying to use is not reliable. So what can we do? We couldn't postulate a better distance. So we thought, okay, let's try to learn a distance. What would be a good distance between two channel state information measurements? This brings me to the next topic, which is distance learning. How can you actually learn a distance? One thing that we came up with is that in wireless communication systems, we measure the channel very frequently, dozens or possibly hundreds of times per second. And we know that if we look at successive measurements, they are correlated, or typically very correlated. So the idea is to use this property that successive measurements are correlated in the following way. Let's say that let me consider three measurements. The first two, indexed by I and J, they are successive or almost successive. And I have a third one, which is measured much later, let's say, a few minutes later, or, or possibly it's coming even from another user or something like this. So, so here I'm trying to define a distance. So I don't know yet what I put behind this distance here, but I know that this distance, at least I expect it to fulfill this inequality, which says that the distance between these two samples should be smaller than the distance between this sample and that one, which is completely unrelated, right? So all I'm saying is that successive samples should be more similar than non-successive samples. This gives me this inequality. And I'm going to use this inequality to actually drive the estimation of a distance. So how can we formalize this? I'm again using this neural network architecture, and my definition of the distance between x and x prime is going to be f theta of x minus f theta of x prime. Theta is some parameter that I have yet to optimize. And this is actually a Euclidean distance, but it's a Euclidean distance in the latent space, which has low dimension. So this is what I want. I want my distance to fulfill this inequality, the one I showed before, and I know that I can generate a whole bunch of triplets of measurements that will very likely fulfill this inequality, because I only need to generate triplets for which the first two elements are successive measurements. They will be closed, and the third one is coming from much later or much earlier. And based on this, I can build a cost function, which is that one. And if I optimize this, I'm going to actually train my neural network to learn a meaningful distance between channel state information samples. And here what I do is I kill two birds with one stone, because I also perform dimensionality reduction. Because once I have trained this neural network to learn a distance, it's also generating a reduced dimension representation as a byproduct. So let's see how this works. Okay, this is one way to represent the operation that I just described. So I'm going to present some experimental results, trying to validate actually this approach. We managed to get access to some measurements from commercial equipment, a massive MIMO base station mounted on a rooftop with 64 element rectangular array, operating in the 3.5 gigahertz band. We measured the uplink CSI continuously at 200 samples per second. And we were also, so the base station is fixed. The user is mobile in this campus environment. We are also collecting GNSS location just to get some ground truth, right? So here's so this is the area in which the mobile user was moving, and this is actually this spaghetti thing is all the locations that were visited by this moving user. So the idea was to crisscross the area many times in order to generate sufficient data to have a meaningful representation of the manifold we are hoping to discover there. So we collected 4 hours of data, close to 3 million samples. And if you apply dimensionality reduction to this data, you can get a bunch of channel charts. So, this is the GPS map for comparison. I didn't mention that there are more dimensionality reduction techniques than the few ones that I presented. One of them is actually, you probably know it, principal component analysis. It's a linear approach. This is the channel chart that we obtained with PCA. That's the autoencoder and the Siamese networks that I have also shown. UMAP is a more advanced algorithm, and And the last one is the triplet networks that actually rely on the distance learning approach that I presented. So visually, we see that probably the triplet networks are the best choice here because so here the data set is colored up still arbitrarily based on the 4 quadrants of the GPS representation. So you see that these 4 quadrants for this channel chart, they are pretty much contiguous, and they are also well separated. Which is not the case for the other approaches. In fact, we have also so this is just visual inspection. We can numerically evaluate the quality of the result, and what we have found is that the last approach, the triplet networks, is actually the one that performs best on this data set. Some more experimental results now with a simpler data set. So here what we did is we went around this building multiple times. So it's like it was a cyclic measurement campaign. And there was one variant here. Sometimes we would drive on the left of this bush, and sometimes we would drive on the right of this bush. There's this small eye here, and the corresponding channel chart that we get on the right, I think is very nice because it captures very well the cyclic topology of the measurement, and I think we can also we can identify also this small eye here. So I think it's it shows that this self-supervised method can give a quite accurate representation of what's happening on the ground, purely based on the channel that we measure and nothing else. So the question, I hope I can have a few more minutes to conclude, but I want to discuss what we can do with these methods. So the applications. Essentially, one thing that we have in mind is to use channel charting as a pseudo-positioning tool. So the idea is to have a 2-step process. The first one is a long-term process, and is the one I have just described. You collect a lot of data, you apply dimensionality reduction. For example, you train a neural network, and then you stop training this neural network. But you keep getting new channel state samples, right, in real time. So what you do is that you can feed these channel state samples in real time to your pre-trained neural network, and what you will see is a pseudo position of the user which is moving in real time on the channel chart. So the idea is that there are many applications where this can actually replace the true geographical location. And geographical location can be hard to obtain, especially on the network side. So it's of course, as the end user, you can always open Google Maps, and your phone knows where you are, but your operator does not have access to this information. Your operator does not necessarily know very well where you are. On the other hand, the channel chart can be computed very conveniently on the network side, based on the uplink channel state information. So that's the thing that we want to propose, to use this channel, this position on the channel chart as a pseudo position. And if you think of what can be done with it, first you can use it for radio resource management. Let's say predicting trajectories of users and pre-configuring the network, maybe anticipating the cell handover, these kind of things. You can use it for millimeter wave beam management. You can do the channel chart on the lower frequency where you have massive MIMO arrays, and use that channel chart to pre-position the millimeter wave beams. You can do device grouping if you want to do device-to-device communication, proximity detection. During COVID, proximity detection was a big thing. geofencing. So, if you there may be ways to map some real geographical features onto the channel chart. Like, let's say, I know that this is a shop and this is some area where no one should go, and so on. So in that way, you can implement geofencing on the channel chart. Network diagnostic. You can detect areas where users systematically lose connectivity. General context awareness, actually, if you are building a digital twin and you don't have access to real location information, this can be a good surrogate. Localization. So the idea there would be to enhance classical localization methods using self-supervised approach. So it would not be self-supervised anymore. It would be probably semi-supervised. So let's say I have a channel chart, but for some positions I know I have the real geographical position. So this allows me to rotate my channel chart back into the true geographical coordinates. Maybe some channel modeling, channel simulation, things like that. So at the moment we are trying to extend this approach and to make it more practical. One thing that we are looking at in particular is how you can do a channel chart with constrained memory. Because if you want this channel charting operation to run on a base station or maybe a Wi-Fi access point, it's clearly not practical to store all the CSI data. If you have a few seconds to waste, just do the math. Number of samples per second times number of coefficients, number of subcarriers, and so on, and you quickly end up filling any kind of hard disk you may have. So we have to be able to do this without storing all the data. So we have to do something like core set selection or some other approach, and this has to be done in real time, right? So we have some preliminary results on this. We are still trying to enhance these approaches. Another interesting extension, in my opinion, is what can happen if you have multiple base stations. Typically, in a cellular network, there is not a single base station. There are multiple base stations, and in general, they have overlapping coverage area. Of course, partially overlapping. So there are many positions where given UE would be within reach of two base stations. In that case, you can think of measuring the uplink CSI to the first base station and to the second base station almost simultaneously for the same UE. So if each of these base stations is computing its own channel chart, you know that for some samples, not all, but for some samples, when the user is in the common coverage area, you would have some points in the first channel chart that would correspond to another location in the second channel chart. And the idea is that how can we reconcile these two informations to build a joint channel chart? And of course, you don't want to do this with only two base stations. You want to do this with an arbitrary number of base stations, and then you may get something like this. I mean, I'm not going to explain all these sets, but this is what you need to do if you want to generalize this to more than two base stations, right? And try to align all these channel charts. Okay, I hope you have found this interesting. If you did, and you want to know a bit more, I just want to point out to a couple of online resources. The first one is this website, channelcharting.github.io, which we maintain together with Professor Studer in ETH Zurich. It has extensive bibliography and source codes and data sets about channel charting. And the second one is the Chaser project, which is currently funding this work, and we will post some news and new results. So if you want to follow, this is a good starting point. And finally, some to play with practical channel charting with real data. The University of Stuttgart has put online some data sets, including some channel charting tutorials. So that's also a very good starting point for this for these works. Thank you for your attention.
Long live India and France friendship.